Assalamu alaikum. This is lecture number 1 of week 10 for the course of electronic devices and circuits. Please remember that this recording merely covers the ideas that are going to be discussed during the class. So this will be brief and we'll have a detailed discussion, and if any derivation is required, it will be done during the class to be held tomorrow. So last class we were talking about rectifier circuits, and rectifiers are a very important building block in the electronic power supply. We had a look at the block diagram of the power supply, in which you have an input transformer at the input. Its purpose is to provide isolation from the AC mains, as well as it reduces the voltage levels from, let's say, hundreds of volts to few tens of volts, so that the voltage levels cannot destroy the diodes that are connected in the rectifier circuit. But the point is that the input voltage at the input of rectifier is still a purely AC signal. The DC level of this voltage is 0. When the signal passes through the rectifier, it only allows the positive half cycle to pass, or negative depending on the way the diode is connected. Then the output signal at the output of rectifier will be a pulsating DC signal whose DC value or average value is non-zero. It can be positive or negative depending again on the way diodes are connected, or diode is connected. But this signal has a non-zero DC value, but the ripple in the DC voltage is large. The way output voltage varies is large. So to reduce the ripple, we add a filter block. It reduces the ripple, so output voltage at the filter stage is having a decent amount of DC value, but it has low ripple. We cannot directly connect load to the filter output, because if we do so, the ripple will become dependent on the load value. Like if the load is larger, a high value resistor, the ripple might be small. But if the value of load is small, that is, we want to have a larger current drawn for the load, the ripple will basically increase. So to make the output voltage ripple independent of the load, what we do is we add a voltage regulator stage. So in the beginning we have only covered the diode rectifier circuit. That was a half-wave rectifier. We did some derivations for the half-wave rectifier. One part that was not covered was the peak inverse voltage. Peak inverse voltage basically means that if the diode is reverse biased, what is the largest negative voltage that can appear across the diode? Like if we talk about the forward bias voltage, we are taking the difference of the voltage on the anode side with the voltage on the cathode side, which is typically in the forward bias a positive value equal to V gamma, which is roughly 0.6 or 0.7. But when we are talking about the reverse voltage or the inverse voltage, we are actually looking at the voltage difference between the cathode node and the anode node. It is the voltage at this node minus the voltage at this node, which is the voltage difference is the potential, reverse potential across the diode. If we carefully look, the cycle at which the diode will be reverse biased is the negative half cycle, and during the negative half cycle the diode is off, so there is no current through the diode, and the only single path for the current to flow is through the resistor. So if the current through the diode is 0, the value of the voltage across the resistor will be 0 because of the Ohm's law. Therefore, if we consider the bottom node as a reference node with 0 volts, then the voltage at this node will also be 0. Therefore, for the largest amount of voltage that could appear in the reverse direction across the diode will happen when this node is at the lowest voltage. So if we assume that the sinusoidal input voltage has a peak value of Vp, then during the negative half cycle, the voltage on the anode side will be minus Vp. And if we take the difference of the two voltages, 0 on the right hand side and minus Vp on the left hand side, so the difference will be 0 minus Vp equal to Vp. So if the secondary winding voltage is having a peak value of 10 volts, the maximum reverse voltage or peak inverse voltage across the diode for this half wave rectifier circuit will be also 10 volts. Now we move on to the full wave rectifier circuit. You can see that the rectifier circuit here, the output voltage is only non-zero during the positive half cycle, whereas in the negative half cycle the value of the output voltage is 0. So we are actually only using half of the input cycle to create a DC voltage at the output. Now we move on to the full wave rectification. So as for the half wave rectifier, the rectifier is driven by the secondary winding of the transformer. So given the transformer turns ratio, you could find the secondary winding voltage, which will be a sinusoidal voltage as we said, and we could apply that to a full wave rectifier. So now full wave rectifier basically are of two types. So the first type that we will cover right now is the rectifier with center tap transformer. So you see that we have a transformer. It's a special type of transformer which has 3 terminals, and the center tap is generally connected to the ground or the reference node. So the distinctive feature of this transformer is that for the input cycle, we have a sinusoidal voltage at the input on the primary side. There are 2 polarities of the output voltage. When the input cycle is positive, then the first winding of the secondary side has a positive voltage on the upper side. The bottom or the center tap is connected to ground, whereas the other side is at a negative voltage. So if input voltage is, let's say, 5 volts, the secondary input voltage is, let's say, whatever volts, and it gets transformed into the secondary winding with, let's say, 10 volts here, then at that time minus 10 volts will appear here. If the voltage increases to, let's say, 12 volts sinusoidal, then the voltage over here will be minus 12 volts, and so on. So you can see that when the input cycle is positive, this side is at a higher potential than ground, and this side is at a lower potential than ground. It means that the diode D1 during the positive half cycle will be on, it will be forward biased, whereas the diode D2 will be reverse biased, it will not be on. Therefore, the path for the current to flow will be through this ground, through this positive Vs, positive cycle Vs, through the diode and into the load. If you look at the maximum voltage that can appear at the output, it's the peak value of the input side minus the forward voltage drop across diode D1, which is typically V gamma or 0.6 or 0.7 volts. Therefore, if the input voltage is 10 volt peak sinusoidal signal, then the maximum value of the output voltage will be roughly 9.4, 9.3 volts. So when the input cycle becomes negative, this voltage will become negative, whereas the other voltage will become positive because it's a drop of Vs. So if the input is 10 volts, if the voltage here is minus 10 volts, this side will be at plus 10 volts. Therefore, during the negative half cycle, the diode D2 will conduct, whereas the diode D1 will be reverse biased. Now, in this way, the current will flow in this direction, that this is the voltage drop, this side the diode gets a forward voltage drop, and then it goes through R and back here. So the current is flowing in this direction. You see that the direction of the current through the resistor is unchanged, whether the diode D1 is forward biased or the diode D2 is forward biased. If you look at the output voltage here, you see that it's the negative of the input voltage that appears here. Therefore, this input is negative. Therefore, the output voltage will also be positive. This can be easily explained through writing a KVL, which we will do in tomorrow's class. But the idea is that the full wave rectifier with center tap transformer converts the input cycle into 2 half cycles, both of which provide a positive voltage at the output. Therefore, the diodes conduct for a longer time, and there's a positive voltage appearing in each half cycle, positive half cycle as well as the negative half cycle. Now we have to look at the peak inverse voltage in this case. So we could pick any of the diodes, D1 or D2. Let's say we consider the diode D2 for the peak inverse voltage. We will consider the cycle in which the diode D2 is reverse biased, which is the positive half cycle. So in this case, when the voltage at this node is most positive and the voltage at this node is most negative, in that case the largest reverse voltage will appear, because as I said, for the half wave rectifier, the peak inverse voltage is the, or generally the inverse voltage is the potential difference of the cathode side and the potential of the anode side. So if this voltage is at the maximum and this voltage is at the minimum, in that case the peak value of the inverse voltage will appear. So during the positive half cycle, this voltage will be Vp above the ground. This diode D1 is forward biased, so the output node voltage will be Vp minus V gamma. Whereas at that time, the voltage on the anode side of diode D1 will be minus Vp. So if we now calculate the difference of the two voltages, this side is at Vp minus V gamma and this side is at minus Vp. Therefore, the difference will be Vp minus V gamma minus Vp. So the peak inverse voltage for this topology will be 2 times Vp minus V gamma. So now if we compare the pros and cons of the two rectifiers that we have studied so far, the half wave rectifier and full wave rectifier with center tap transformer. So you see that obvious benefit of the full wave rectifier is that it is conducting basically twice as much as compared to the half wave rectifier. So this is one benefit of the full wave rectifier here. The drawbacks, however, is that the diodes, the number of diodes is double. So you need two diodes, and more importantly, you need here a diode with a larger PIV, larger peak inverse voltage rating. So these diodes will be expensive as compared to the diode of the half wave rectifier. We could also calculate the average value. So the average value will be roughly double. We can derive it the way we derived it for the half wave rectifier. We may be doing it in the class as well. But in general, the idea is that since the diode is conducting for twice as much, diodes are basically conducting for twice as much, and the output voltage is there for both half cycles, the average value of the output voltage will be roughly double in this case as compared to the half wave rectifier.